Hello, and welcome back. In the next few sessions, we're going to talk about the two primary ways we have of looking at electrical signals. We can look at electrical signals in the time domain, as you would with an oscilloscope, and we can also look at them in the frequency domain, as you would with a spectrum analyzer. The mathematical tools we have for relating these two domains include the Fourier transform to translate from the time domain to the frequency domain, and the inverse Fourier transform to translate from the frequency domain back to the time domain. We will plunge into these relationships shortly, but first, let's look at the building block known as the Fourier series. Any periodic signal with a period that we will call capital T, whose fundamental frequency f0 equals the reciprocal of t, can be expressed as a Fourier series, which is a theoretically infinite sum of sinusoidal components whose frequencies are integer multiples of the fundamental frequency f0. The series is named for French mathematician Jean-Baptiste Joseph Fourier, and I recommend reviewing the section called On the Nature of Sinusoids in Part 1 of the Math Sessions. Let's look at the basic building block of the sinusoid, which we will call x of t. It is defined by its amplitude a, its period capital T, and a phase angle theta. The temporal frequency f0 is the reciprocal of the period, and the angular frequency omega naught is 2 pi times f0. By its very nature, the sinusoid is a repeating or periodic waveform, and this allows us to determine its average or mean value by taking a time-averaged integral over a single period, given by 1 over t multiplied by the integral of x of t, starting at any arbitrary time, given by lowercase t1, and integrating to t1 plus capital T. We plug in our expression for x of t, take the integral, evaluate it at its limits, rearrange terms, and because omega naught equals 2 pi divided by the period t, we can substitute 2 pi for omega naught t. Adding 2 pi to any sinusoidal argument puts you right back where you started, which allows us to remove the 2 pi term from the argument. Now we're left with a sine term minus the same sine term, which leaves us with 0. Thus, the integral of any sinusoidal function over a period equals 0. We can see this by inspection because the sinusoid is symmetric about the 0 line. The area under the curve for the positive part of the cycle is balanced by the area under the negative part of the cycle, giving a net area of 0 for a full cycle. Now we've demonstrated it mathematically, leaving no room for doubt, and it is an extremely useful result for Fourier analysis, as we'll see. Now let's look at the average or mean power of a sinusoidal waveform. If x of t is the potential across a resistance R, the instantaneous power is given by the square of the potential divided by R. The average power is given by 1 over R times the average value of x of t squared, which equals 1 over R times 1 over t multiplied by the integral of x of t squared over a period. If x of t is the current through a resistance R, the instantaneous power is given by the square of the current multiplied by R. The average power is given by R times the average value of x of t squared, which equals R times 1 over t multiplied by the integral of x of t squared over a period. In either case, the average power is proportional to the average or mean value of x of t squared. The root mean square, or RMS value, is defined as the square root of the mean of the square of x of t. The RMS value of a voltage or current is the equivalent DC value that would dissipate the same average power, P average, in a load resistance R. And frequency components are commonly expressed as RMS values. So, let's look at the average value of the square of our sinusoid x of t. We'll make use of this trig identity that states that cosine squared of b equals 1/2 times 1 plus cosine of 2b, and make that substitution. We move the constants out front and take the integral. 1 integrates to t, and cosine of 2 omega naught t plus 2 theta integrates to 1 over 2 omega naught times the sine of the same argument. We plug in the integration limits, and we see that for the t term, our starting time t1 cancels and is therefore arbitrary, leaving just the period capital T. In the first sine term, again we can substitute 2 pi for omega naught t. Adding an integer multiple of 2 pi to any sinusoidal argument returns the original argument, leaving a sine term minus the same sine term, which leaves us with 0. Thus, the phase term theta cancels and is also arbitrary. The period terms t cancel, giving the average value for x of t squared of a squared over 2, and the RMS value of x of t equals the familiar a over the square root of 2, which equals approximately 0.707 times a. Recall from the math sessions that a sinusoid can be represented as a linear projection of circular motion along the unit circle in the complex plane with a constant angular frequency omega. The circular motion in the counterclockwise direction is expressed as e raised to the power of j omega t, and per Euler's formula, cosine omega t is the projection onto the real axis, and j sine omega t is the projection onto the imaginary axis. The convention we follow is that counterclockwise motion is called a positive frequency component. Circular motion in the clockwise direction is expressed as e raised to the power of minus j omega t. This is the complex conjugate of e to the plus j omega t, and clockwise motion is called a negative frequency component. Cosine of omega t can be expressed as 1/2 times the sum of e to the plus j omega t plus e to the minus j omega t, and j sine omega t can be expressed as 1/2 times the difference of e to the plus j omega t minus e to the minus j omega t. Thus, a sinusoid can be expressed as the sum or difference of equal contributions from positive and negative frequency components. Now let's revisit the average power of our sinusoid with what I'll call exponential method 1, using our exponential substitution for the cosine function. We have established that the phase term theta is arbitrary, and we will set it equal to 0 for simplicity without any loss of generality. We'll multiply this expression by itself to take the square. The a over 2 terms square to a squared over 4. First, we'll multiply through by the e to the minus j omega naught t term, which is the conjugate of e to the plus j omega naught t. Then we'll multiply through by the e to the plus j omega naught t term, which is the conjugate of e to the minus j omega naught t. We multiply through, which means we add the exponents. E to the 0 equals 1, and we make that substitution. Now we take the time-averaged integral over a period. We have established that the start time t1 is arbitrary, and we will set it equal to 0 for simplicity, again without any loss of generality. We evaluate the integrals, plug in the limits, and again we can substitute 1 for e to the 0 and 2 pi for omega naught t. E raised to the power of j times any integer multiple of 2 pi equals 1, which gives 1 minus 1, zeroing out the second term in each set of brackets. This is a very important result. This says that the integral of any sinusoidal or imaginary exponential function over an integer multiple of periods equals 0. We will come back to this presently. The period t terms cancel, and we're left with a squared over 4 plus a squared over 4, giving a total average value for x of t squared of a squared over 2, and an RMS value for x of t equal to a over the square root of 2. These are the same answers that we got for the sinusoidal method, as they must be. Some key observations from this. Multiplying any imaginary exponential by its own conjugate cancels the exponential component, leaving a constant that averages over a period to itself. And as we just noted, multiplying any other frequency component by that same conjugate leaves another imaginary exponential that integrates over a period to 0. This seems rather useful. Now let's revisit the average power of our sinusoid with what I will call exponential method 2. We'll call the positive frequency term x plus of t, and we'll call the negative frequency term x minus of t. We get the conjugate of each term by flipping the sign of the exponent. When we multiply x plus of t by its conjugate, we get a squared over 4 to give the average power contribution of the positive frequency component. And we get the same result when we multiply x minus of t by its conjugate. We add the terms to get a total average power of a squared over 2, which is the same answer as before, as it must be. From this, we see that the power contribution from any frequency component, positive or negative, is given directly by multiplying by its complex conjugate in a single step. This only works due to the findings of the previous analysis. But now that we know this, we can apply this simpler single-step approach. The preceding discussion was all about calculating the average power of a sinusoidal waveform with a known amplitude. But what if you didn't know the amplitude of a given frequency component and wanted to find it? Let's find out. Let's multiply our expression for x of t by the conjugate of the positive frequency component and take the time-averaged integral over a period. We'll move the constants out front, and we see that the exponents in the first term cancel to 0, leaving 1 as our first term, and the exponent of the second term doubles to minus j times 2 omega naught t. As we noted earlier, the integral of any imaginary exponential function over an integer multiple of periods equals 0. The 1 integrates over a period to the period t, the t terms cancel, and we are left with a over 2, which is the amplitude of our positive frequency component. Now let's multiply our expression for x of t by the conjugate of the negative frequency component, and again take the time-averaged integral over a period. The exponent of the first term doubles to plus j times 2 omega naught t, and the exponents in the second term cancel to 0, leaving 1 as our second term. As before, the exponential term integrates to 0, and the 1 integrates to the period t. The t terms cancel, and again we are left with a over 2, which is the amplitude of our negative frequency component. Thus, when you multiply by the complex conjugate of the desired frequency component and take the time-averaged integral over a period t, you get the amplitude of the desired frequency component only, and all other frequency components integrate to 0. And that is the crux of Fourier analysis. Monsieur Fourier showed that any periodic signal of period t, that is, with a fundamental frequency f0 equal to 1 over t, can be expressed as an infinite sum of sinusoidal components at integer multiples of the fundamental frequency, also known as harmonics. And this is called a Fourier series expansion. We start with the fundamental, then we have the second harmonic at twice the fundamental frequency, the third harmonic at 3 times the fundamental frequency, and so on out to infinity. Note that the sum goes from minus infinity to plus infinity to include both positive and negative frequency components. The coefficient of the fundamental component, C1, is obtained by multiplying x of t by e raised to the power of minus j omega naught t, and taking the time-averaged integral over the period t. The coefficient of the second harmonic, C2, is obtained by multiplying x of t by e raised to the power of minus j times 2 omega naught t, and taking the time-averaged integral over the period t. The coefficient of the third harmonic, C3, is obtained by multiplying x of t by e raised to the power of minus j times 3 times omega naught t, and taking the time averaged integral over the period t. And so on, where the coefficient of the nth harmonic, Cn, is obtained by multiplying x of t by e raised to the power of minus j times n omega naught t, and taking the time averaged integral over the period t. This is our expression for general Fourier series expansion coefficients, and in general, they can be complex numbers with magnitude and phase. We can use Euler's formula to express them in their real and imaginary components with cosine and sine terms. The magnitude and phase for a given coefficient are given in the usual manner for complex numbers. This set of frequency components and their coefficients gives us the frequency domain representation of our signal of interest. Thus, the Fourier series expansion provides the frequency content for periodic waveforms. This is indeed extremely useful, but what about a non-periodic waveform? How do you represent that in the frequency domain? Well, you start by pretending that it is periodic. You define your sampling interval as the effective period t, and your effective base frequency f0 equals 1 over t, and your base angular frequency is 2 pi f0, or 2 pi over t. Applying the Fourier series expansion technique, we can obtain coefficients for a set of discrete peaks at harmonics of omega naught. Then we extend our sampling interval in both directions toward minus infinity and plus infinity, and that will reduce our base frequency omega naught toward 0 to the point where we can call it a differential frequency d omega. Looking at our expression for Cn, we multiply both sides by t and extend our integration limits to plus and minus infinity. We define this expression to be the function capital X of n times omega naught, which is the amplitude of our nth frequency component. We'll come back to this. When we take the limit as t approaches infinity and omega naught goes to 0, we get a continuous function capital X of omega, which equals the integral from minus to plus infinity of x of t times e raised to the power of minus j omega t times dt. And this is called the forward Fourier transform that gets us from the time domain to the frequency domain. This is, in theory, a continuous function instead of a set of discrete peaks. Let's go back to our original time domain signal, x of t, expressed as a Fourier series sum of its individual frequency components. Recalling that omega naught equals 2 pi over t, we can rearrange terms such that omega naught times t divided by 2 pi equals 1. Thus, we can multiply our expression by omega naught t over 2 pi as a way of multiplying by 1. We can move t and omega naught inside the sum, and from the previous slide, we had defined t times c sub n to be capital X of n times omega naught, which is the amplitude of the nth frequency component. Again, as we take the limit as t approaches infinity and omega naught approaches 0, we get that x of t equals 1 over 2 pi times the integral from minus to plus infinity of capital X of omega times e raised to the power of j omega t times d omega. And this is called the inverse Fourier transform, which gets us from the frequency domain back to the time domain. A time domain signal represented by lowercase x of t and its frequency domain representation, capital X of omega, are called a Fourier transform pair. This will wrap up our introduction to the Fourier transform. In the next session, we'll look at some real-world implementations, including the discrete Fourier transform and the fast Fourier transform. See you then.